Glad to see you again. We're going to do something a little bit different for a short while. We're going to look at actual math, you might say. Get away from the applications temporarily because some of these things are helpful when we're actually working with applications. This time we're going to be talking about increasing and decreasing functions. When do they do that? And we'll see that's not too hard to do. Let's see where, there we go. Need to set up the pen, right? And I'm ready to go. All right, so here are the three things we're going to focus on. Testing for increasing and decreasing functions, finding the critical numbers, which will allow us to find where that function is increasing or decreasing. Then we'll hit a real-life problem. It's always good to do that. A function is increasing when the graph moves up. Now, this is pretty simple, really. Just remember that when we look at almost any picture, we're looking at the x values getting bigger. We're scanning left to right. So as we're doing that, is the graph going up or down? If the graph is going up, then it's increasing. If the graph is going down as we move to the right, then it's decreasing. Real simple. This more complicated looking thing down here, this just says that the first x value you pay attention to is on the left, and the second x value that you pay attention to is further to the right. Sticking with that, we then say we've got a function that's increasing, at least for a while. That's what this means. It means here are the y values. The first y value is not as big as the one to the right. That's all it means. And the decreasing means as you're going from left to right, that the y values are getting smaller instead of larger. Nothing more. Here's a picture to give you an idea. This looks similar to a parabola, but not quite. It's got a flat bottom. But the idea is you can see as you're going from left to right that the y values are decreasing for a while until it gets to this point. The y values stay the same, they're constant, and then after that x value, the y values are going up, or they're increasing. Check out the intervals here. Remember that the squared off parentheses is called a bracket, and that means that this number right here is included in the interval. Whereas, like with the infinity or negative infinity, that means that number, if it's a number, is not included. Now, we've been talking about derivatives for months now, and when we take the derivative of that function, that can help us find out whether a function is increasing or decreasing at a particular place. And it's very simple, really. First of all, you take the derivative of the function, so that f function has to be differentiable on that interval where you're going to check it. Take the derivative, and if that derivative in that interval is positive, then it's increasing. Very simple. Y prime is positive, means your function itself is increasing. if the derivative is negative, like this, all you have to do is check for the sign. You don't care about the magnitude of the actual derivative, only whether it's positive or negative. If it is negative in a certain interval, which means y prime is a negative number, then that means your function is decreasing. And last of all, and the simplest of all actually, if your derivative is 0, that means the y values are not changing. So y prime, where's my, here we go, y prime is 0, then our actual function is constant. There, that's closer. All right, next, let's take a look at a particular example. Our example for this one is f of x equals x squared, our familiar parabola, basic parabola. We want to show that it's decreasing from negative infinity to 0 and increasing from 0 to infinity. So we start by taking the derivative of the x squared. Remember what the function is up here. Here we go. Take the derivative, and on the open interval, notice that from negative infinity to 0, all those numbers are negative. So just pick a number if you don't instantly see what it is. Negative 10, for example. What's negative 10 going to do with 2x? Well, negative 10 is going to give you negative 20. Another negative number. You always get a negative number because you're taking a positive times a negative. Bingo. That means it's decreasing on that interval. So how about a positive one? On the right-hand side, in this interval right here, where's my cursor again? There we go. On this interval, every x you pick is positive, and when we take 2 times that positive number, positive times a positive is a positive, and that implies, even without seeing the picture, that the function is going to be increasing on that interval, 0, infinity in this case. Critical numbers. This helps you get the intervals themselves. So this is very important, as you might expect for something called critical. So before you were given 2 intervals, and you had to tell whether the function was increasing or decreasing. What if you had to figure out what the intervals were? Different story. Well, notice that if you've got a function like this one right here, while it's increasing, the derivative is positive. When it's decreasing, the derivative is negative. And to go from one of those intervals to the other, at some point, it needs to be either 0 or, in this case, undefined, because the tangent / derivative here is undefined. So those are 2 indications you've got a critical number. You've got a critical number when the derivative is 0, but also when the derivative is undefined. So keep in mind, number 1, number 2. to get critical numbers. So here's a list of things for you to do. If you want to find where the function is increasing or decreasing, first find the derivative. Where's my cursor again? There we go. Find the derivative. Then find the critical numbers. Remember, those are where it's either 0 or doesn't have any value at all. It's undefined. Use those to get the intervals, because those numbers will sort of chop the number line into slices. In those intervals, just test one. Just one test value, anything you like in that interval, and see what you have for the sign of the derivative. It doesn't matter whether it's -6 or -60, it's only about the sign. Positive one means you've got an increasing interval. A negative one means you've got a decreasing interval. That's all you need to do. So we've got another example here, example number 5. And we've got a function to play with here. We want to find the open intervals on which it's increasing or decreasing. So what's the first thing we're going to do? Find the derivative. So we'll differentiate that. Notice that 2/3 coming out front. Leave this alone. Reduce that original exponent by 1. And then the derivative of the inside, because we've got the chain rule, folks. Not only the power rule going on here, but also the chain rule. Never forget the chain rule. There's a bit of simplification. That makes it look a little bit cleaner. So, from that derivative, look back here if you need to. From that derivative, oops, what's that doing? There we go. Okay, first of all, the derivative is going to be 0 if the numerator is 0. So you can just set for x equals 0, and 0 is going to be one of your critical numbers. There you go. Second, the denominator being 0 means you've got an undefined derivative. And this is the derivative down here. So you can set this equal to 0 and find out where it's undefined. So what you've got is, this is from the derivative being 0, and these two are from the derivative being undefined. Those are your critical numbers. Now, what you do is, either on paper or in your head, consider a number line. Here we have 3 points. Got a point at 0, got a point at 2, you got a point at -2, and these critical numbers cut the number line into 4 different intervals. You've got numbers over here, you've got numbers in here, and here, and here. Next, it gets real easy here. All you have to do is pick some number in here, any number at all. -3 if that's your favorite number. Put that negative number into the derivative and see whether it's positive or negative. Positive means increasing, negative means decreasing. Next, check out this interval. Pick any number in there you like. -1 would be an obvious choice here. Put it in the derivative till you get a positive or a negative answer. It won't be 0 because you already have that as a critical number. So it's just positive or negative. Go over here to the third interval. Put one of those numbers, maybe the 1 because that would be simple. Put that into your derivative. You have a positive or a negative. And fourth, take a number over here, maybe a 10. Put that in your derivative. Is it positive? Does it give you a positive derivative or a negative one? Once you get the test intervals, it's easy, very easy. And here are the numbers that the person that made these slides used. From -infinity to -2, they picked a -3. They put that -3 into the derivative, and they don't care how big it is, just the fact that you get a negative answer out of that. That means the function itself is decreasing. In the second one, from -2 to 0, they picked a -1, obvious choice, put it into the derivative, it was positive, so the function is increasing there. Third interval, they picked a 1, another obvious choice. Your derivative turns negative. That means your function is decreasing in that area. And then last of all, in the fourth interval, 3 is an easy choice. I mentioned 10, it doesn't matter, just so it's in the interval. And check to see whether it's positive or negative. In this case, it would be increasing, so your function is increasing. Here's what it looks like picture-wise. It doesn't hurt to graph that on your calculator if you can. But that's just verification of all the things that you just found. The two should match, and it's a nice feeling to look at it and see that what you got on paper matches what's on the graph, and the graph matches what you got on paper. Notice that the converse isn't true. You can have a function increasing everywhere even though it's not positive at every point in the interval. What's that mean? Well, look at this one. The x cubed minus 3x squared plus 3x is increasing everywhere. The derivative gives you that. Only one critical number at x equals 1. Test intervals. So your initial impression might be, well, it's increasing on one, decreasing on the other, I expect. However, it's increasing everywhere. So keep that in mind. Do the tests. Don't do the test on one and assume that it's going to alternate between the two, as in our first example. That's not necessarily true. You have to find the intervals and you have to test each one of the intervals. But inside each of the intervals, you can choose any number you like within that interval. So here we go with an application. Let's check this out. We've got cost and revenue functions for one of the games by a toy distributor. First of all, you want to find the open interval on which the profit function is increasing. Notice you don't have the profit function. Notice also one thing before we move on, that the domain is restricted, and this should make total sense to you, particularly in the first case. You can't have a negative number of games, so 0 totally makes sense. 6,000, I couldn't tell you for this one, but perhaps each month the machines that you're using or the people you're using can't produce more than 6,000. So that's a possibility. So the profit equals revenue minus cost. There you go. Put those two functions together. Remember what they were? There they go. Revenue minus cost. Not cost minus revenue. Revenue minus cost. There we go. That's the profit function. Simplify that. And then what? To find the interval, we're going to find the marginal profit, alias the derivative, set it equal to 0, and solve for x to get those critical numbers. Now notice this profit function doesn't have a denominator, so you won't have to be concerned about an undefined derivative. So it'll just be where the profit function equals 0. So there's your derivative. I set it equal to 0, solve for x, and there's your x, a little bit of calculator work, and x equals 3,000 games. Now what does that do? That gives you intervals. That splits the number line into two sections, but remember, our domain was only 0 to 6,000, so we've got two intervals. 0 to 3,000 and 3,000 to 6,000. Now, take that derivative that we had on the previous page, take any number at all between 0 and 3,000, the first interval, and put that in the derivative. See whether it's positive or negative. Well, as they checked, they don't show you the check, but on that interval, there we go. On that interval, if you put any of those numbers in P prime of x, the marginal profit, you get a positive answer. So that means from 0 to 3,000, the profit is increasing. Hooray, right? It's your business. You want more profit. On the interval 3,000 to 6,000, put one of those numbers in. Maybe 2,000, or excuse me, maybe 4,000, 5,000, or something in between if you feel adventurous. Put the number in for P prime of x, the marginal profit, and you should get a negative. That means after 3,000 games, the profit starts decreasing. Oh, darn it. You don't want that to happen. There's a picture of what's going on. It actually shows you all three functions. The original cost function in blue, profit function in dark black, and there's the revenue function in the gray. So you can see how the two are connected. If you spend a little bit more time, you can actually look at the cost function. Where am I? Look at the cost function and look at the revenue function and take a value of x. And if you subtract the two, you end up with a value from the profit function. Not necessary, but you might. And that's it for now. See you next time when we take this a little bit further. But remember to keep your critical values, make your intervals, find out what's happening with the function. See you next time. Bye-bye.